Welcome to the viewers. Now we discuss one important theorem. The theorem is continuous image of a connected space is connected. Then how to prove this theorem? So to prove this part of the theorem, let us consider x1 tau 1 be a connected space and x2 tau 2 be any topological space. We also assume if there exists a function phi from x1 tau 1 to x2 tau 2 be a continuous function now we have to produce or we have to show phi of x1 is connected. Let us consider phi of x1 be disconnected. It is our object. If we assume it is disconnected and we find and conclude that a contradiction, then we show it is connected. So we assume it as disconnected. And with this on the assumption, we are proceeding and draw a contradiction. So let us consider phi x1 as disconnected and let phi of x1 is equal to, if we considering any two functions open sets g1 and g2 in x2, then phi of x1 will be given as g1 intersection phi of x1 union g2 intersection phi of x2 and where g1 and g2 are open sets in x2. So in this way we assume, if you draw a figure, if it is a topological space of x1 tau 1 and if we find another topological space say x2 tau 2 and if there is a mapping from x1 tau 1 to x2 tau 2, that is phi, and if this function g1 and g2 exist, and then these images of g1 and here it is g2, and only this kind of portion, that is we find phi of x1 is equal to g1 intersection phi of x1 union g2 intersection phi of x2, in this way. And if we conversely find that's inverse of this function, that is phi inverse, and here it is find that's this result transferred to, we find it here phi inverse of g1, and here we find another function that is phi inverse of g2, and only this result, that is we find it here x1 is equal to phi inverse of g1 union phi inverse of g2. So in this way we find x1, but from this figure it is easily appears that it is a connection, they have some connection, that's why these things happen. So we assume in this figure, and g1 g2 are open set in x2, it is clear, and this result only phi of x1, we are already getting these positions, and which is absolutely in x2, images of x1 we are getting. And now these g1 g2 are open sets in x2 such that g1 intersection phi of x1 and g2 intersection phi of x1 in this area, this particular shaded region, are a pair of non-empty disjoint open sets in phi of x1. We already given in some representations. And next we find by the definition of continuity, that's why phi inverse exists. So by the property of continuity of phi, we have phi inverse of g1 and phi inverse of g2 are open sets in x1, we already find, and then from the result we have phi of x1 is equal to g1 intersection phi of x1 union g2 intersection phi of x1. We find x1 is equal to phi inverse of g1 union phi inverse of g2. Already we give pictorial representations, and this is our concept where RHS members are non-empty and disjoint. It should be a disconnection, but our assumption, that means x is disconnected, x1 is disconnected, that is x1 is disconnected but x1 is not disconnected because we taking the topological spaces x1 tau 1 is connected, that's why it is not disconnected, but here we find it is disconnected, so a contradiction. We have a contradiction. Hence the proof. So in this way we prove this result. A contradiction is drawn here. It is a form of clear disconnection, but it is not the same. x1 is not disconnected, so contradiction drawn. So in this way we prove x1, that is a connection. So continuous image of a connected space is connected. So it is clear have some connection of phi of x1. We end our discussion today. If you like this video, like it, share it. Don't forget to subscribe the channel. Thanks for watching.